Hello everyone. Today we are going to look at derivative of exponential functions y equals e to the power of x. This is 5.1 in your textbook. Number e, or Euler's number, is equal to 2.71828 and it has non-ending decimal places here. So it's an irrational, non-terminating, non-repeating number like pi. Why number e is special? Because derivative of e to the power of x is equal to e to the power of x. Okay, so before we look at the derivative of e to the power of x or do some practice questions, we are going to look at some characteristics of e to the power of x. So in advanced functions, we learned that if we have a to the power of x equals b, so this is in exponential form, we can put it in logarithmic form. And then we get log base a of b equals x. So let's remember, base of the power becomes base of the logarithm. Then other two values switch side when you're converting exponential form to logarithmic form. How about if we have e to the power of x equals y? So if we write it in logarithmic form, then we get log base e of y equals x. But we call log base e a ln, okay? So after this point, you're not going to see it as log base e, but you are going to see it ln. So again, let's remember from advanced functions. If we have log base a of a, so this is equal to 1. Similarly, log base e of e equals 1. But again, log base e is called ln, so ln e equals 1. So another property, if we have f of x equals e to the power of x, derivative of f then will be equal to e to the power of x. How about if we have f of x equals e to the power of g of x? So the exponent is not x, but is a function of x. So when you're taking the derivative of that function, then you get e to the power of g of x. So you keep it as it is. Then you multiply this by the derivative of the exponent. So this is the chain rule. Again, in advanced functions, we learned that y equals 10 to the power of x and y equals log base 10 of x are inverse functions. Okay, so similarly, let's remember log with base 10 is called just log x. So if the base is 10, we do not write it. Similarly, e to the power of x and log base e of x, so basically ln x, are also inverse functions, and they are symmetrical about y equals x line. So now we are going to sketch e to the power of x and ln x here. Okay, so let's make a little table of values here, x and y. So let's take three values for x, -1, 0, and 1. Then if we substitute it here, so when x is -1, e to the power of -1 gives you 1 over e. E to the power of 0 gives you 1. E to the power of 1 gives you e. So 1 over e, if you do it with your calculator, so we get around 0.37, and again e is around approximately 2.7. Okay, so if we sketch those values here, so -1 and 1 over e, 0 and 1, and 1 and e, so we get this function. Okay, and let's remember, if there is no transformations, we have a horizontal asymptote at y equals 0. So when you're graphing an inverse function, you just interchange the coordinates. So we're going to do the same thing for ln x, because we know that e to the power of x and ln x are inverse functions here. Okay, let's do that. So negative 1 and 1 over e becomes 1 over e and negative 1. 1 over e and negative 1. 0 and 1 becomes 1 and 0. And 1 and e becomes e and 1. So if we sketch this, we get this curve, okay? And as you see, these are symmetrical about y equals x line. So we said that e to the power of x has a horizontal asymptote at y equals 0. Then ln x will have a vertical asymptote at x equals 0. Okay, so let's write some properties of e to the power of x and ln x. Let's look at the domain of e to the power of x. As you can see, like all other exponential functions, it is xer. Okay, and the range of it is going to be yer and y greater than 0. So let's write domain and range of ln x. So let's remember, if the original domain of the original becomes range of the inverse, and the range of the original becomes domain of the inverse. So I can just apply here and say range of ln x is yer, and domain of ln x is xer, x greater than 0. But also we could use this sketch, because this is y equals ln x and this is y equals e to the power of x. We could also use the graph to write those. Okay, so e to the power of x passes through 0 and 1, and ln x passes through 1 and 0. Asymptotes. So e to the power of x has an horizontal asymptote at y equals 0, and ln x has a vertical asymptote at x equals 0. Let's remember another property from advanced functions. If we have 2 to the power of log base 2 of x, so this is equal to x. Okay? Then if we apply the same thing to e, so if we have e to the power of ln x, again, let's remember e to the power of ln x is log base e of x. Okay, so this is equal to x. Okay, and similarly, log base 2 of 2 to the power of x equals x. So let's remember the power rule for logarithms. So this is what you do, right? So you take the exponent, put it in front, and then you have log base 2 of 2 here, x times log base 2 of 2, and this is equal to 1, so x times 1 gives you x. So therefore, similarly, ln e to the power of x equals x, applying the same rule. Okay, so as you see here, we have the graph of e to the power of x. E to the power of x is unusual because it is the exact same as its derivative. This means that for every x, the slope at that point is equal to the y value. Okay, so let's analyze this for a second. So let's say we are here at the point 0 and 1. If we draw a tangent at this point, okay, the slope of this tangent will be same as the y coordinate of that point. Similarly, let's look at point 1 and 2.72. So if we draw a tangent at that point, the slope of that tangent will be same as the y coordinate of that point. Therefore, e to the power of x is a special function. So let's look at example 1. So this is just practicing a number e, okay, and how to use the calculator with number e. So as you see, for my calculator, we see e to the power of x, okay, so I'm gonna use that. It always asks for the exponent, So I'm just going to put here 4, and if you just need to look at the value of e, let's say let me put 1 here. So this will give you the value of number e. Now I'm going to look at e to the power of 4. So this gives 54.59. 54.598. Okay, so let's look at e to the power of negative 3.3. Again, just getting used to the calculator, okay, with this number e. So you have negative 3.3, so you get a decimal value 0.037. Okay, so let's look at ln. In advanced functions, we learned that we only have logarithm with base 10, but actually you also have logarithm with base e, so you also have ln in your calculator. Okay, so if you need to calculate ln 74.45, that gives us 4.31. Okay, how about ln negative 2? So ln negative 2, as you see, will give you a math error. So we cannot have a negative value inside, okay? So it was the same thing with advanced functions. With any logarithm, you cannot have a negative number inside the log or ln. So this doesn't exist. Okay, so ln e, we already learned that this is same as log base e of e, and this is equal to 1. How about if we have ln e to the power of 1.45, and again log base e to the power of 145. So again, using the power rule of the logarithm, okay, this can be written as 1.45 times log base e of e, or 1.45 times ln e, and ln e is 1, so we end up with 1.45 here. Okay. How about if you have e to the power of ln 3 squared? So this is e to the power of ln 9, okay, and this is going to be equal to 9 using the shortcut. Again, let's remember, if you have e to the power of log base e of 9, okay, so this gives you 9. Example 2, solve for x. If we have ln x equals 7, okay, so we can put this in exponential form. Let's again remember, ln x is log base e. So if you put it in exponential form, you get e to the power of 7 equals x. Okay, and after this point, you can just do it with your calculator, and we get 1096.63. Okay, so we have another one. We are going to solve for x. 7 equals 2 times e to the power of 1.5x. So before solving this, you need to isolate the exponential piece here. Okay, so that exponential piece is multiplied by 2. So you need to get rid of 2 first, divide both sides by 2. Okay, then you can take the log of both sides. That's what we did in advanced functions. Let's say if you have 3 equals 2 to the power of x, so how do you solve this? We were taking the log of both sides, okay, and then use the power rule. On the right side, we were getting x times log 2. Then to isolate x, divide both sides by log 2. So you would get log 3 over log 2. That's how we were doing it. So we could do the same thing here, use log, but actually if the base e, then we take the ln of both sides. So you can take the log with of both sides with any base. We use log with base 10 because our calculator did not have any other base for logarithm. But actually now we know that it also has log with base e, which is ln. So instead of taking the log of both sides, we are going to take ln of both sides basically. So ln 7 over 2 ln e to the power of 1.5x. Now again I'm going to use the power rule. So we are going to get 1.5x times ln e on the right side, and we know that ln e equals 1. So we get ln 7 over 2 equals 1.5x. Then we can divide both sides by 1.5. Then we get x equals ln 7 over 2 over 1.5. Okay, and we can just use our calculator. Ln 3.5 divided by 1.5. So 0.835. So x is 0.835. All right, let's look at number 3. So I'm going to make a second video for that.